Hello, welcome to the tutorial. Let's wait for a couple of minutes. If someone wants to join, they can join and then we'll start. So before we start, if you want to have some doubts cleared, feel free to ask and we'll wait for another couple minutes so that if someone else wants to join, they can join. And then we will begin solving some problems. So feel free to unmute your mic and ask questions. You can also type your doubts in the chat box. Hello, ma'am.
Good evening.
Good evening, ma'am. Okay, so okay, so uh, in the last session we were discussing some classical mechanics like Lagrangian and Poisson brackets, and that is where we ended our last session. But today's problems are not that related to those concepts. So I think we can start solving a few problems, and then in the end of the session, then we can go back to our discussion of classical mechanics and how how do we bridge the gap between classical and quantum mechanics using the Ehrenfest theorem. Okay, is that okay?
Yes, sir.
Yeah, okay. Good. So before I begin, let me just ask one more time. Is there any particular problem that you want me to answer, or should we just start solving some problems that I have with me? Like if you have any doubts, feel free to ask. Okay, if not, then I guess we are all set to begin with the first problem. Okay, so we are given a Hamiltonian here, this one, and it is also given that alpha is a real number which has dimensions of energy. Phi 1 and phi 2 are normalized eigenstates, of a Hermitian operator A that has no degenerate eigenvalues, and the question is if H is a projection operator or not. Okay, so first of all, what is a projection operator? Yeah. So projection operator, correct. Projection operator must satisfy two properties. First one being hermiticity, so it should be Hermitian, and second one is idempotency, that is it should be idempotent. Hermitian means that P dagger should be equal to P, and idempotent means P squared is equals to P. Okay, now let's have a look at the Hamiltonian H. It is given that H is alpha, which alpha is a real number, times phi 1, phi 2 plus phi 2, phi 1. Yeah. Is this Hermitian? Is this Hamiltonian Hermitian? If we take H dagger, what do we get? We get alpha star, and then so this first term will give us phi 2, phi 1, plus phi 1, phi 2. Okay. Okay. Why? Because we know that if we have any two eigenstates A and B, and if we take the dagger, then this becomes B A. Yeah. So here the ket of A will become the bra of A, and the bra of B will become the ket of B. Yeah. So we applied this same thing here. Okay. Also, we know that alpha is real, so this alpha star will be just alpha. So our H dagger will be alpha, and writing the second term first, we basically get the same thing. Okay, and this is nothing but H, which means our Hamiltonian satisfies the hermiticity, and we can say that the Hamiltonian is Hermitian. Now let's check the second condition, which is idempotency. For that we need to take H squared, right? H squared. So H squared will be alpha squared, and then this multiplication. So when we multiply, what we will get? We will get phi 1, phi 2, and then phi 1, phi 2. Okay, so this will be the first term, and second term will be phi 1, phi 2, phi 2, phi 1. Similarly, the third term will be phi 2, phi 1, phi 1, phi 2. Yeah. And finally, we will have phi 2, phi 1, phi 2, phi 1. Okay. So what have we done? we had this Hamiltonian, so we have squared it, so we'll have a square of this thing, right, which is written here. So 5152 multiplied by 5152. Notice here we have 5152 and 5152. Then we'll have a square of this thing, 5251 and 5251. Then we'll also have these cross products. Just 1 second. Yeah. Okay. Then we'll have the cross terms where we multiply 1 with 2 and 2 with 1, and they will give us these two terms. Okay, so now notice that in the problem it is given that they are normalized eigenstates of a Hermitian operator A that has no degenerate values. So what this will mean? This will mean that phi 1 and phi 1, this is equals to phi, sorry, phi 2, phi 2, and this is equals to 1, whereas phi 1, phi 2 or phi 2, phi 1, this is equals to 0. So here we have these four terms, meaning this first term and this second term, they will go to 0, and these two will go to 1. Okay, and then our h squared will become alpha squared, and this is phi 1, phi 2. Okay, so this is 0, so this is phi 1 times phi 1 plus phi 2 times phi 2. Okay, so this is our h squared, and clearly if we, okay, let me write down h again. So h was alpha phi 1 phi 2 plus phi 2 phi 1. So clearly h squared is not equals to h, right, which means that the idempotency condition is not satisfied. Therefore h is not a projection operator. So the answer is B, no. Okay, any doubts?
Just one minute. Can
Yes.
we take the figure of cat A, bra B? So you have written cat B, bra A.
Yes.
So this dagger, will this come should it be equal to cat B dagger, bra A dagger? Is it like
Yes.
that?
Yes. So if you remember, we had the reversal rule. So the second term comes first, right? So let me write it down here. So xy dagger means we have y dagger, x dagger. Yeah.
Yes.
So this b will come first, and if you take the conjugate, so the bra becomes ket and ket becomes bra.
What about dagger?
That dagger is changing this bra to ket. So
Okay,
it's the adjoint. So it is in dual space, right? One is we have bra space and ket space. So this dagger essentially is taking you from one space to the second space. Okay. Okay. Any other doubts? No. Okay. Okay, then let's go to the second one. Okay, so the second problem is we are given a harmonic oscillator and its Hamiltonian. And then the question is that we are also given the position and momentum operators in Heisenberg picture. So our position operator looks like this and our momentum operator looks like this. Okay, and then we are asked what will be the value of this commutator. So the momentum commutator at two different times, t1 and t2. Okay, so we are given what a momentum operator looks like at some time t. Now we have to find out this at t1 and t2, and then we have to find out its commutator. Okay, so let's do it. So first thing what we should do is expand this commutator, right? So this commutator so this will be nothing but this p cos omega t1 minus m omega x sine omega t1, right? So this is the first term, and comma p cos omega t2 minus m omega x sine omega t2, right? So this is the second term. Okay, I have just written the value of the momentum operator for 2 times t1 and t2. Okay, wait a second. Yeah, okay, okay. So this is what we have. Now there is this linearity relation, which is that if we have a commutator of the form a plus b comma c plus d, it expands as a comma c plus a comma d plus b comma c plus b comma d. Okay, also we know that the momentum operator's commutator will be 0 and the position operator's commutator will also be 0, right? So for example, if this is a, okay, let me write a b c d. So clearly the commutator of a and c will go to 0, right? So this this term will go to 0. Similarly, the commutator of b and d will go to 0. So this term will also be 0. Okay, and we'll only have the cross terms. So essentially what we will have is, so we will have p cos omega t1, right, and its commutator with minus m omega x sine omega t2, right? This will be the first commutator, and similarly we will have the second one where we will have m omega x sine omega t1 and its commutator with p cos omega t2. Okay, so we'll have these two terms. The other two terms, they just go to 0. Okay, so what will this give us? So let's take the constants outside. So this will give us minus m omega cos omega t1 sine omega t2 and the commutator of p comma x. Similarly, this will give us minus m omega sine omega t1 cos omega t2 and x comma p. Okay, now we know the commutator relations A. Yeah, answer is A. Okay, so we know the values of x comma p. So this, we know that this x comma p, this is just iota h cut. So this p comma x, this will be minus iota h cut. Okay, so then what we can do, we can simplify these things. So let's take this iota h cut m omega, let's take this outside. So inside we will have cos of omega t1 sine of omega t2, right? And here we'll have minus sine of omega t1 and cos of omega t2. Okay, so this is a, basically this is a trigonometric identity, right? If you remember, we have a trigonometric identity which is sin A cos B minus cos A sin B, which gives us sin A minus B. Notice that we have an additional minus sign here, so we can take one minus sign here, make this minus, make this plus. So then what we will have, we will have minus iota h cut m, sorry, m omega, and this becomes sine of omega t1 minus t2. Okay, so let's see if it matches. Yeah, so the answer is A. Okay, any doubts here? Yes, no? Okay. Okay, so if you notice, there is one interesting thing. Notice that what we are doing essentially, we are finding out the commutator of momentum at time t1 and at time t2. Generally, so okay, let's do a special case. So the special case will be if t1 and t2 are same. So basically at the exact same time, some, let's say sometime t0, then basically this pt1 comma pt2, this will go to 0, as it should be, right? Because this sine 0 is 0. Why? Because momentum operator will commute with itself. Now notice what is happening. So when we are taking this commutator at different times, then what happens is there is some uncertainty that comes in, right? So there is some temporal uncertainty. Okay, so essentially if we are measuring a momentum at time t1 and then later at some time t2, this relation which shows that they do not commute with each other essentially gives us some idea that there will be some uncertainty that is induced in the system, that we can't now predict. So essentially, if we know what the momentum is at time t1, because this thing is not zero, then we cannot easily predict what will be the momentum at some later time t2. Okay? Okay. Okay. Now this is the second part of the problem, where we have to find out the commutator of position operators. Yeah. So again, we'll do the same thing. So we'll expand expand this. So this commutator, this will simply become x cos omega t1 plus b by m omega sine omega t1, and its commutator with, so the second term will be x cos omega t2 plus b by m omega sine of omega t2. Okay. Again, we know that this is of the same form, a plus b comma c plus d, right? Again, the commutator corresponding to the terms, let's say this is a and this is c, so the commutator corresponding to this term will give us 0, because there we will have x comma x. Similarly, for these two terms, this one and this one, we will have p comma p, right? So this will also be equals to 0. Then the remaining terms will be, so the first term will be s cos omega t1 and its commutator by sine omega t2, right? So this is the first term, and then the second term will be p by m omega sine omega t1 comma x cos omega t2. Okay. Then again, let's take out these constant terms outside, right? So what we'll have cos omega t1 sine omega t2 upon m omega x comma p plus sine omega t1 and cos omega t2 upon m omega and p comma x. Okay. Now this term is just iota h cut, right? And this term is minus iota h cut. So let's take out this factor which is common, iota h cut by m omega, and inside we will have cos omega t1 sine omega t2 minus sine omega t1 and cos omega t2. Okay. So again, using the same identity, what will we have? We will have, again, a minus sign will come, m omega, and this will be sine of omega t1 minus t2. Okay, so I attach cut by m omega and sine omega t. So option B here. Okay. So again, same thing. We see that position, the position operator also does not commute at different times, which essentially means that if we know position at time t1, does not mean that we will be able to predict precisely the position at time t2. Okay. Any doubts in this? I can't hear you, sorry. Can you try again? No, your voice is breaking. Sorry, I can't hear you. You can type in the chat box. I can't hear you. I'm sorry. Yeah, yeah, sure. I'll wait. Please type. Meanwhile, I'll just flash the next problem if someone is interested. I hope my voice is clear and my video is also fine. I hope I don't have a network problem. Yeah? Can we say that this problem is a hint of Ehrenfest theorem? Uh, mm, yeah, you can say a hint of, but not exactly. So one thing is that in Ehrenfest theorem, we have to consider the expectation values, right? So we consider not the operator values, but the expectation values. So for example, instead of x, we should have the expectation value of x. So generally this term goes in the Ehrenfest theorem, which is the average value of your operator, right? And then the second thing, that the commutator that is defined there is generally with h, right? So any commutator with h, like let's say h comma a or something. So you are right, you are correct in some way. If we did the basically, what this means is, if you perform the same thing in classical mechanics, then you will get a zero, this thing, basically zero commutation, meaning that in classical mechanics, if you know a position at time t1 and momentum at time t1, then you also can predict in principle what will be the position and momentum at some later time t2. So this problem just gives you an essence of quantum mechanics. It's more kind of related to the Heisenberg's uncertainty principle, if you think about it, that the delta x between two different times and the delta p at two different times, that is not zero essentially. So there is some uncertainty when we calculate the position and momentum at two different times. Okay. Later we will solve one problem related to Ehrenfest theorem. So yeah. Okay. Any other doubt before we move on? No? Okay, good. Let me. Okay, so please go through the question and I will take a quick break. Okay. So what are we given? We are given a system of two spin half particles, such as electrons, and it is also given that they are in a state with total spin quantum number is equals to 0. So the total spin quantum number is 0. Now the Hamiltonian is defined as this, where A is a positive constant, S1, S2 are spin angular momentum operators, and we are asked to find out the eigenvalue of the Hamiltonian. Okay, so we are given a lot of things. Let's take it step by step. So first of all, we are given a system of two spin half particles. Okay, so we have two particles, and spin half meaning they have two possible values. They can be either up or down, right? The next thing that is given is that the total spin quantum number S is 0. So if we add them up, we should get 0. So if one is up, the other should be down. If the one is down, the other should be up. Okay. Finally, we are also given that the Hamiltonian looks like this, where A is some constant, and S1 and S2 are spin angular momentum operators. And then we are asked what is the eigenvalue of this Hamiltonian. Okay. So let's write the Hamiltonian first. So the Hamiltonian is H as A times S1 dot S2. Yeah. And we have A greater than 0. The total spin quantum number S is written as, sorry, S1 plus S2. S1 plus S2. Okay. So this would imply that the value of S squared, yeah, will give us S1 squared plus S2 squared plus 2 S1 dot S2, right? And then we can write this S1 dot S2 like this. So half of the entire thing, S squared minus S1 squared minus S2 squared. Okay. So what are we able to do? We are able to write the value of S1 dot S2 separately in terms of S squared, in terms of S1 squared, and in terms of S2 squared, right? Now,
Sir, how
yes,
is S1 S2 equal to S2 S1?
because they commute with each other.
Okay.
Yes. Okay.
Thank you, sir.
Yeah, okay. So let's proceed. Yeah, let me just write that this S1 and S2, this is 0. Okay. So they commute. So because they are spin half particles, that means their eigenvalues S1 is half and S2 is also half. Okay. And when we operate, let's say S1 squared, okay, on some wave function, so the eigenvalues that we get are of the form S plus 1 h cut squared. Okay. Similarly, for S2 squared, we get the same thing. So S plus 1 and h cut squared. Okay. And what is S? Okay, so this will be, sorry, this will be S1 S1, this will be S2 and S2. Now S1 is half and S2 is also half. Okay, so they are same. If we plug in this, so half and 3 by 2, so this gives us 3 by 4 h cut squared. Sorry. Yeah, and this also gives us 3 by 4 h cut squared. Essentially, so okay, so let me just quickly tell you what we are doing. We need to find out the value, the eigenvalue of this thing, S1 dot S2. But what we don't know the eigenvalues of S1 or S2 separately. What we know is we know the eigenvalues of the square of these operators. So we know the eigenvalues of S square, okay, S1 squared, S2 squared. That is why we have converted this S1 dot S2 to this thing, okay. And then here we have calculated for S1 and also S2, and what we are also given that the total spin quantum number is 0. So capital S, this thing is 0. So if we calculate for S squared, then what we get is S squared, sorry, we get S plus 1 h cut squared, but this thing is given to be 0, so this term just goes to 0. Okay, yeah. Now we can just calculate the eigenvalues of this Hamiltonian H. So the eigenvalue of H will be E, and it is simply A times this thing. So multiply with half, and this first term is 0, and second term and the third term, they are both same, 3 by 4 h cut square. Okay, so finally what we will get? We will get A by 2, and this will be minus 6 by 4, and so this will cancel out. Okay, 2, 3. So our energy will be minus 3A by 4 h cut squared. Okay, which means option C. Okay, so basically you will encounter these kind of things when you talk about spin resonance. Yeah, anything you want to ask?
So one thing is I did not understand this part where S1 square gives rise to S1 into S1 plus 1 H bar square. Maybe I do not know the relation, which is why I'm asking.
This one. Okay, okay.
The one in yellow.
Yeah, I got it. So okay, so I think this. Oh, okay. So I think this angular momentum operator is not yet taught in the class, is it? No?
Which is yet to be covered.
I think no, sir.
Okay. I don't know why they assigned me this problem then. So basically, okay, nothing to worry about. So when we have some, okay, so spin is also a kind of angular momentum operator, right? Generally we start with L. Okay, we start with L, and we call that this is our angular momentum operator. And then essentially what we do, okay, so when we study this hydrogen atom problem, for example, so we write the wave function let me remove this thing from here. For a hydrogen atom, when we write the Schrodinger's equation, notice that for a hydrogen atom we have to consider the spherical coordinates, right? So instead of x, y, z, we consider r, theta, phi, right? So what we do is we convert this psi, which is a function of r, theta, phi, we break it into two components. One is the radial component, okay, and then second is the your angular component, okay. Sorry. So our wave function looks something like this, okay. Don't worry, it will be coming in the I hope next week this will be taught, right? So now when we do this thing, then we get our spherical harmonics, right? We get spherical harmonics, and angular momentum is one of the operators which depends on this theta phi. Angular momentum does not depend on r. And using these spherical harmonics, essentially what you will find is that it is that that the eigenvalue of L squared is simply L plus 1 and this h cut, okay, just like here, sorry, h cut squared, okay. So this thing just comes out from this long derivation. Unfortunately there is no short way to derive this thing right now. For now you can just, okay, for this problem you can just take this for granted that whenever we have some angular momentum, any angular momentum, spin or orbital, the eigenvalues of this operator, okay, if it operates on, let's say, some psi, L squared psi, then we get these eigenvalues, L times L plus 1 h cut squared. And this L is actually quantized, so it can have integer values starting from minus m to plus m. This is basically, okay, I am running ahead of myself. So L basically goes from minus m to plus m, where m is your magnetic quantum number. For example, if you have a 2p orbital or any p orbital, forget about 2, then here your then here your L is basically 1. For s orbital, L is 0, okay. And so for this L as 1, we'll have 3 values of m, minus 1, 0 and plus 1, okay. So for a p orbital, for example, you can plug L is equals to 1, and what you will get? You will get 2 h cut squared. So this will be the angular orbital angular momentum corresponding to your electron in a p orbital. Okay. If you don't understand, don't worry about it. This will be covered in the upcoming lectures. This problem, I think, then is misplaced. Okay, nothing to worry about. Let me just again explain what we did. So we had this Hamiltonian S1 dot S2. So what we don't know is the eigenvalues of this operator. What we do know is the eigenvalues of this operator. Okay, we don't know this, but we know this. So we convert this S1 S2 to the square things, right? So notice here we have these square things, and then we have written this simply as this S1 times S1 plus 1, S2 times S2 plus 1, and this is total S times S1 plus 1, okay. Okay. Sorry for this problem. Okay. We can come back to this problem next week when we have studied the angular momentum. This thing. Okay. I guess then let's move on to the Pauli spin matrices. Then this Pauli spin matrices are also something which wouldn't be taught to you. No problem. So let me just write out what are these. So these are some 2 cross 2 matrices. We have 3 of them. So we have sigma x, which is this. We have sigma y, and we have sigma z. Okay. So in case you have not come across these, don't worry. This problem does not require to understand what they mean physically. We can still solve this problem. We just need to know that what are the Pauli spin matrices. Okay, so then let's spend some time and calculate all of them. So what will be sigma x squared? This will be 0 1 1 0 multiplied by 0 1 1 0. Okay, so basically what this will give us, so 0 times 0 plus 1 times 1, this will give us 1, this will be 0, this will be 0, and this will be 1. Okay, similarly for sigma y squared, so this will be 1 because minus iota squared is 1, and this is 0, this is 0, and again minus iota squared is 1. Okay, and finally if we calculate sigma z squared, that will 1 0 0 minus 1, that will also be same identity. Okay. So this is 1 times 1, so and 1 0 0, and minus 1 times minus 1 is also 1. Okay, so all of them are equal to the identity matrix, so all of them are 1, which means that option A is correct. Now option B says sigma x times sigma y is minus iota times sigma z. Okay, so what will be sigma x times sigma y? We will have this thing and we will have this thing. So if we multiply, so here we will have iota 0 and 0, and here we will have minus iota. Okay, and if we take iota outside, we will have 1 0 0 minus 1, and this is nothing but sigma z. So this is equals to iota times sigma z. Now in option B there is an extra negative sign which is coming, so this is incorrect. Okay, similarly we have sigma y times sigma z. Okay, let's find out that one as well. 0 minus iota, iota 0, and 1 0 0 minus 1. Okay, so this will just give us 0 and minus iota and iota and 0. So this is nothing but, okay, this will be minus iota. No, this will be plus iota, but this will also be plus iota, right? Because this minus iota will be multiplied with minus 1. Okay, so this is iota times 1 0, sorry, 0 1 1 0, and this is nothing but sigma x. So this is iota times sigma x, which means option C is also incorrect. And finally, we have option D, sigma x sigma y, which we have already calculated. It comes out to be sigma z. Let's calculate what is sigma y times sigma x. This will be 0 minus iota and 0 1 1 0. So this is 0 and minus iota and 0 0, and this is iota, right? So this is minus iota outside 1 0 0 minus 1. So this is nothing but minus iota sigma z. So we have sigma x times sigma y as iota times sigma z, and sigma y times sigma x as this thing. So if we add these two, like here, we should get 0, right? So sigma x sigma y plus sigma y sigma x, this is iota sigma z minus iota sigma z, which is 0. So option D is in fact correct. Okay, so what we get from here is that we have this. So one thing about Pauli matrices is that the square of the Pauli matrices should be equal to 1, and then the second thing, okay, this should have come out to be this thing, and this should have come out to be this thing. So you can see that there is some kind of a cyclic relation. Okay, so if we multiply x and y, we are getting iota times z. Then if we do y times z, we are getting minus iota times x. Okay, so this is what we have. We have this standard cyclic relation. And finally, for option D, we see that their anti-commutator is 0, right? So basically, for any two sigma j comma sigma k, any two Pauli matrices, their anti-commutator is 0, which means that they anti-commute with each other. Okay. So this Pauli spin matrices will also come up when we are dealing with spin angular momentum in later classes, I hope. Okay. Did I miss? Okay. Okay. Another problem which has angular momentum in it, but not necessarily we'll be using the angular momentum operator here. Why? Because the question is more about the wave function than the angular momentum thing. So what are we given? We are given that these are the values of n, l, and m for a hydrogen atom, and the question asks that what will be the value of r at which the radial probability density of the hydrogen atom reaches its maximum, okay, in terms of a naught, and we are given this wave function. Okay, so this is the radial part of the wave function. Okay, so let me first write down this radial part of the wave function. So this is just some constant, right, where a naught is generally called as Bohr's radius, and then it depends upon r like this. Maybe some of you have seen how it varies with r. Okay, so for example, what will be the zeros of this wave function? Meaning, when will this function r12 be 0? Can anyone tell me? Mm, so this r1 comma 2 r will be 0 for r is equals to what value? 0, yeah. So 1 is 0 and the other one?
Infinity?
Yeah, infinity. Correct. 1, so 1 is coming when this term goes to 0 and the other when this term goes to 0. Okay, so this term goes to 0 when r is 0. This term goes to 0 when r is infinity. Okay, also note that r is in our polar coordinates, so r is always greater than equal to 0, right? It does not have any negative values. That is how the polar coordinates are, right? Then we have theta and phi. So let's not worry about theta and phi here. Then basically what I am trying to say is, if you plot this function r, capital R, here as a function of this small r here, okay, so what will it look like? So we know here it is 0 and we know that here also it will
Planck
be 0.
Planck's way, but with the because there you have square like a Planck's law, right?
Yes, but yeah, correct. You must have seen similar curve when you encounter this ultraviolet catastrophe. Yeah. So the Rayleigh Jeans formula looks something like that. And then somewhere here it will have a maximum and then it will go down like this. Exponential decay kind of a function. Right? This thing and here this thing. Which means that here somewhere at some value, let's say r naught, we have a maxima. Okay, and this r naught is what we are supposed to find. So they are asking where the radial probability density of hydrogen atom reaches its maximum. Okay, so for the radial probability density, what we need to do? We need to square this thing, right? And then take the first derivative, put it equals to 0, and then we will have it. So let's do it. So our probability density, let me call that P of R. This is the radial probability density. This is given as, we have a R square that comes here and then mod of R to 1 R square that comes. Okay, so this is how the radial probability density is defined. Okay, so you get an additional R square term. Okay, so basically we have R squared and then this constant, let me call this as some constant C, and then basically what we have 1 R and then we have e to the minus r by 2 a naught and then square of this thing, right? So then we have some constant C prime Okay, and then this will be r to the power fourth and a to the power minus r by a naught. So this half and square, they cancel out each other. Okay, so we will not worry too much about this c prime because this does not have any r dependence. Now let's take the derivative of this function with respect to r, and we know that at r is equals to r naught, this derivative is 0. Okay, so that implies that this derivative of this function, which will give us 4r cube a to the minus r by a naught. Okay, we'll also have one c. Okay, and then we'll have 1 minus 1 by a naught coming out, r4 a to the minus r by a naught, and this thing calculated at r is equals to r naught will be basically 0. Let's take out these things common. So basically we have r naught cubed e to the power minus r by a naught. This is again r naught, and inside here we will have 4, and here we will have r naught by a naught, and this thing is 0. Okay, so note that we can have this r naught going to 0. That will give us one solution, the first term. Okay, so if this is 0, then our derivative becomes 0. If this is 0, again our derivative becomes 0. But we have already considered these 2 points. So 0 and infinity are these 2 points. We know that here the probability is not a maximum but a minimum, right? Here the probability is a minimum. So we are only left with one choice, and that choice is that 4 minus r naught by a naught is 0, or r naught is 4 times a naught. Okay. If you want to check if this is really a maxima, we can find out the second derivative and see that the second derivative is coming out to be negative. But you can do that as a homework if you want. Essentially, we know that it has 3 points where the first derivative is 0. This is the first point, 0, and this is the second point, infinity. We already know that the probability here is 0, right? Our electron in a hydrogen atom cannot be inside a nucleus, and it cannot be at infinity. It has to be somewhere in between. So the maximum probability comes at this point, which is 4 a naught. Okay, so okay, let's just go back to the problem quickly. What we were given is n is equals to 2 and L is equals to 1, which means that our electron was a 2p, was in a 2p orbital. Yeah, if it were in a 1s orbital, this value comes out to be a naught, which is the Bohr's radius. Okay, 1s orbital. Okay, let me just draw a very simplistic. So this is our nucleus. Let's say this is n equal to 1, and let's say this is n equals to 2. Okay, so this is 1, and this is then therefore a naught, and then this one is coming out to be 4 a naught. So here, so the probability of an electron is maximum at a distance 4 a naught when it is in the second orbital. Okay, that is what this problem gives us, which also makes some sense, right? Because the second orbital is little far from our nucleus. So for the first orbital, if it is a naught, then for the second one it should be higher than a naught, and it generally varies as squared, right? So it goes to 4 a naught. Okay.
Can you
Sir,
please
what
Yes.
pause?
is the use of having, sorry, someone else is speaking.
No, no, please continue.
Okay, what is the use of having n equal to 2, l equal to 1 and ml equal to 0 in this question? We did not use them anywhere.
It's just yes, we did not. Okay, we did not use them directly, but what? Uh, let's say we were not. Let's say we were not given this thing. Okay, we were not given this thing. So here this 2 corresponds to your n. Here your 1 corresponds to your l. Okay, there is no other use. The only use for this n and l is to determine what your wave function should be. So if your particle, if your electron is in a 2p orbital, its wave function is of this form, the radial part. The radial part of the wave function is of this form. Suppose this was not given in the problem, we could have looked up what the wave function looks like for a 2p orbital, which is exactly this, right? And then we could have solved the problem further. So they have given us both the things. They have given the values of n and l, but they have also, for our convenience, given the wave function directly. If they wanted, they would not have just given the wave function. Then we would have looked it up, what is the wave function for a 2 pi orbital, and then we would have solved this problem. There is no other use. Only use is in determining the wave function.
Okay, sir.
Yes. Yes, ma'am. You wanted to ask something?
Yeah, see here it is ml is equal to 0,
Yeah.
right? So L is equal to 1, we can have ml is equal to minus 1, 0 and 1.
Yes.
And all for all three values of ml, the shape will be like this only.
Yes.
It is called dumbbell, I think. Dumbbell shaped.
Yes. The p orbital.
Yeah. But what is the difference in shape when we take different values of ml? M minus 1, 0 and 1.
So
I just
the yeah, so the shape remains the same.
something like that.
Sorry.
I read sometime back that there are some orbitals called sigma orbital and pi orbital when we consider different values of ml.
Those are actually when you consider bonding between two atoms. So then you can have sigma bond and pi bond. That is little different from this
Okay.
context. So
Acha.
here ml being 0, minus 1 or plus 1 will just give you the orientation of the dumbbell. So it can be oriented along the z axis, the y axis or the x axis. Okay.
Here we consider the spherical coordinates. I mean, again we are considering x-axis, y and z.
it
But
just it just comes out to be that way. Okay, so the shape, okay, let me just draw our axis. Okay, let's say this is x, y and the z axis is coming out. So the dumbbell shape looks like this. Yeah, so this is our p orbital. Now it there are basically three possibilities for its orientation. Okay, still you can notice that this is a something kind of a spherical shape, right? This is not a rectangular or a cubical kind of a shape, but its axis, right? The axis about which it is positioned, that is x-axis, right? So this corresponds
yes,
to one of the values. Let's say minus 1. That does not matter. And similarly, if it is oriented along your y-axis, it can be oriented like this. Okay. Let's say this corresponds to your m is equals to plus 1, and if it is around your z-axis, that can correspond to m is equals to 0.
see, z-axis is a special space, special, it,
No, it okay, generally it's just like a convention, right? So generally this okay, this is called magnetic angular momentum, right? M, that's why its
hmm.
name is M. So generally, when we apply a magnetic field, we consider, okay, the field is applied along z direction. Yeah, that's why we just give it some special treatment. You can say the field is applied along x direction, and then you can change your values of m accordingly. Okay,
So
doesn't matter.
when they are all same.
Sorry.
Otherwise, if there is no external magnetic field,
Yeah, they
then
are same. They are
but
basically same. Yeah.
okay.
Mm. Okay. Okay. That's why in the, even if you look at this wave function, right? If you look at this wave function, it only has 2 and 1, which corresponds to n and l, right? It only corresponds to n and l. There is no m dependence here. Your m becomes significant only when, I mean, m is significant otherwise also, but the direction, okay, so should we consider 0 or should we give some special treatment to m is equals to 1? That only becomes significant when we have a magnetic field. In
Okay,
absence of a magnetic field, all three are equally same. The energy of all three is exactly the same.
okay, they are degenerate.
Yes, they are degenerate. Exactly. Hmm. Okay. So next problem. Uh, okay. Before going to the next problem, let's have a quick 30 seconds break. Okay. Yeah. So let's solve this one. And this is the problem that I mentioned earlier, which will be related to our Ehrenfest theorem. So as you can already see that we have some time derivative, and we have a time derivative of the position operator, right? So what is the time derivative of position? It's generally velocity. Yeah. So let's see how we already know what this thing looks like in classical mechanics. D. I have to check. I think it's B, but we'll check. Okay. Anyway, before coming to the answer, so what I was saying, classically we know that this dx by dt is just velocity, so it is just p by m, right? Where p is our momentum. We know p is mv. So here, for example, if you look at option B, where we have dr by dt, so classically I think option B is correct. So we have to now see if quantum mechanically also this relation is true. So what we are given? We are given Hamiltonian. Okay, we are given Hamiltonian in terms of this p squared, and there is some potential v which is a function of r. So what we are asked? We are asked the Heisenberg equation of motion for the position operator r. So essentially how our position is changing with time. Okay. So what is the general equation? Okay, first thing that we should note is that there is no, that this thing is 0, right? There is no partial derivative, okay, of r which depends on time. Okay, so then we know that we can write the equation of motion like this. So our dr by dt will be nothing but 1 by iota h cut r comma h. Yes. Now let's evaluate this commutator. Let's put the value of the Hamiltonian which is given to us in terms of p and v. So this will become, so r remains as it is, and here we will have p squared over 2m plus v, which is a function of r, right? Now since v is a function of r, so its commutator will go to 0, right? So r comma v of r, this commutator will go to 0 because both have this r dependence. So the only term that will be left is this commutator of r with p. So okay, also we know that if we have a commutator of this form, this we already discussed in the previous classes. Let me just again write for sake of completion. Yeah, so here if this is okay, doesn't matter. So what we have here, we have this p square term, right? So this dr dt, we already have this 1 by iota h cut here, and then what we'll have is, we'll have this 1 upon 2m coming out, and then we will have r comma p squared. Yeah, this thing, and the second commutator which is between r and v of r, that will go to 0. Okay, so basically we have two commutators, first one is this and second one is 0. So I am not writing the second one for now. Now using this equation, using this identity, let's solve this commutator, right? So r, we have already done this one before, but anyway let's do it again. So r comma p squared, this becomes r comma p and a p here plus p here and r comma p. Okay, so this is iota h cut and this is also iota h cut, so this becomes 2 times iota h cut p. Okay, now we can substitute this back. So what we will get, we will get this dr dt is 1 upon iota h cut into 2 iota h cut p over 2m, right? So this cancels out and this cancels out, and essentially what we are left with is this thing. So finally dr dt is simply p by m. Okay, and the classical analog is when we generally write dx by, okay, we can write r, doesn't matter, we write dr by dt, and that is our momentum p by m, right? Because this is v, right? And m will cancel out simply. Yeah, okay, so option B is correct. Okay.
One thing you started by saying that the partial derivative of capital R with respect to t
Mm-hmm.
is zero. Is zero.
Yeah.
Can you explain that?
So, hmm. So we are not given, uh, basically we are not given any direct time dependence of R. Anything that is coming because of this uh, p squared by 2m term. So generally, okay, so if you remember the equation for any operator A, and then we had plus sign or minus sign, something like that, yeah. So if so here, because we are A is not given as a function of time directly, so we have just considered this term to be 0.
Sir, also you mentioned the partial derivative of r with respect to time is zero initially in this problem.
Yeah. If we
Uh,
don't, if we, okay, if we don't consider that, then here everywhere there will be this additional partial derivative term, here, here, and again here, right? So you can think of this, that if R does not have any direct time dependence, then in that case your dr by dt varies as just your p by m. If there is some direct time dependence that is given to you of R, then basically this relation will not hold true. Okay? So it's more like an assumption that we have to take.
Any example in which we can have for an explicit time dependence and then otherwise indirect time dependence.
Mm, I mean, okay, so
Maybe we can say that R and T are two orthogonal axes. That's why they don't have any direct time dependence. Is it like that?
yeah, it can be. So that can be one case. And for a time dependence, let's say if, for example, if it is a harmonic oscillator problem, right? Then we have to consider the time dependence of R, right? Because that is changing with time directly. Because we can write R as some sine function, and that time we have to consider this. Okay, so why in the first place we had to take this assumption? Because if you look at the options, clearly there is no second term, right? It's only one term. There is no partial derivative term here. Mm, to be very frank with you, they should have mentioned that this thing, that this that you need to solve this for the assumption that our R does not have any direct time dependence. So you should consider its partial derivative to be 0. I only assumed this partial derivative to be 0 because they didn't have any option where there is some partial derivative. So it's like a hidden assumption that we had to take. Basically, what this problem wanted us to understand is that our quantum mechanics and classical mechanics can both give us the same thing for velocity if there is no partial dependence of r on time t. I think that is the takeaway. Okay. Okay. So I think next, yeah. Okay. So this is a again a problem about hydrogen atom, and they are asking about degeneracy when we take into account the spin of the electron. Okay, and they are asking about the first excited state. So I don't know if we are taught this thing, so let me just mention very quickly that any state of a hydrogen atom is defined by three quantum numbers n, l and m, and the energy is only a function of n, right? So energy is only a function of n. It goes something like this. Okay, doesn't matter, exact form doesn't matter. So energy is determined by n. Okay, and then the value of L, it goes from 0 to uh, n minus 1, and the value of m goes from minus L to plus L. Okay, so our ground state will be n is equals to 0. Okay, let me write here state, the value of L, value of L, and the value of n. Okay, so for ground state our n is 0, then here we can have only one possible value of L, which is 0, and again only one possible value of this. Sorry, n is 1.
N is one, yeah.
N is 1, yeah, sorry. L is 0 and then m is 0. Okay, so this is the ground state. And okay, and this is the, so this corresponds to our 1s orbital. Okay, for the first excited state, okay, for the first excited state, n will be 2. So L can now have two values. It can have 0 and it can have 1. For 0, m will have only one possible value, but for 1, it will have three possible values, 0, minus 1, 0, and plus 1. So this corresponds to our 2s and this corresponds to our 2p orbitals, right? So you can see there are three of them, 1, 2, 3. Okay, and does not matter where our electron is, because our energy depends only on n, it is independent of L and m. So if we want to find out its degeneracy, we have to count how many possible states are there. So there are actually 4 possible states. So first state will be when, okay, so n is always 2, right? So L will be 0, m is 0. This is first possible state. Second state, 2, now this is 1, minus 1, 2, 1, 0, and 2, 1, plus 1. So these are the 4 states. Notice that n everywhere is 2, so they have same energy. All 4 of them will have same energy, and that is what is important. Why? Because they are asking the degeneracy. Okay, and what we have identified that there are 4 possible states, right? Next thing that they have also mentioned is that we have to take into account spin of the electron. Okay, which means we know that electron has a half spin. So each
Up
of
and
these
down.
state, yeah,
Up
each
and
of
down,
these
yeah.
state can be occupied by 2 electrons. So if I draw these states like this, 1, 2, 3, 4, all of them have same energy, and the exact value of that energy will be minus 13.6 by 4 eV, whatever this value comes out to be, and we can fill these with 8 electrons, up down, up down, up down, and up down. So finally, what is the degeneracy? The first excitation of hydrogen atom is how many fold degenerate when we take into account the spin of the electron?
8.
8. Yeah, 8. Okay. If we were asked that we don't have to take into account the spin of the electron, then generally we consider that each state is occupied singly, so then answer is 4. But they have specifically mentioned that we have to take into account the spin of the electron. So we have to multiply by 2. We have 4 states, each can be occupied by 2 electrons. So there is 8-fold degeneracy. Yeah. Okay. Okay. Hmm. Okay, so moving on, we have, okay, okay, two more problems. I'll try to finish them quickly, and because we also have to discuss boson brackets. Okay, second last problem of the day. We have a particle of mass m and charge q. It is moving under the influence of a one-dimensional harmonic oscillator potential. Assume that it is placed in a constant electric field E. Okay, so this is a constant electric field, and the Hamiltonian is given by this thing. Okay, so here you can see that there is some constant electric field along the x direction. Yeah, and this is the Hamiltonian. What we are supposed to find out? We are supposed to find out the nth excited state energy En of this particle. So maybe some of you know the trick that goes into this problem. The trick that goes is, okay, so one thing that we notice immediately, or that we should notice immediately, is that if we look at this term, right, these two, so note that here we have x squared and here we have x, right? So this is x squared and this is x. So this is some type of a quadratic function. If we had some constant here, what we can do? We can do something known as completing the square. So we can complete the square and we can write it as x plus some constant squared, so that when we open this square we will get one x squared term and we will get one x term, and then finally some constant term. Okay, so how do we do that? So let's not touch the first term at all, right? Let's keep it as it is. Now what we want to do, we want to change this second term. Okay, so it becomes half m omega squared, and then let's take this thing x minus q epsilon upon okay, there will be 2 and m omega. So this is x squared and this is x. Yeah, so basically I have taken out this coefficient of x and then I have written the second term like this, squared. Okay, okay, good. So then what we can do, this term remains same, this also remains the same, and now notice that this is of the form x square minus 2ab, right? So if this is a, x is a and this is 2ab, so directly we get that this term is b. So what we can do is we can write this as x minus q e by m omega squared, okay, and this thing whole squared. Now when we will open this, so we'll get x squared, we'll get 2 qe by omega square x, but we'll also get one term which will be plus, okay, which will be this term q squared e squared by m squared and omega to the power 4, right? So we need to subtract this term and then we are good to go. Okay, so if we open this square and then we subtract this term, we'll essentially get back here. Okay, so let's write this as p squared over 2m plus half m omega squared x minus, let's say this is some x naught, and then minus, so this will give us q squared e squared and then upon 2, so this m will cancel out one of the squares and this omega this thing. Okay, so this is now we have, and where x naught is q e by m omega square. Okay, so this is our Hamiltonian h. So we have done some readjustment, otherwise we have not changed anything at all. Okay, if we put in this value of x naught back here, if we open this square, we will essentially get the same thing. But if you notice what we have managed to do, so this term, the last term, okay, this term is this is an energy term, right? Q squared and E squared divided by 2m omega squared, right? This is coming because of our electric field. And this x naught basically means that the origin or the zero of our harmonic oscillator is now shifted, right? So this is a parabolic kind of an equation, and instead of x, now we have x minus x naught, where x naught is nothing but this q and this value of E upon m omega square. Okay, so what essentially what this electric field has done, it has shifted our harmonic oscillator, and it has also added a constant energy shift. So this second term, this is constant, right? So we can directly write our energy. We know that these first two terms will give us h cut omega and n plus half, and this term will give us q square e square by 2m omega square. Oops. Okay, so this is the energy. Let's look at the options. Yeah, option C. Okay, any doubts?
Sir, this problem,
Yeah.
last part,
Mm-hmm.
um, we are taking q square e square by 2m omega square directly into that energy equation. That step I
Okay.
think.
So okay. Uh, let's look here. So our Hamiltonian is an operator, right? When we operate it on a wave function, we get energy eigenvalues, right? Now this p square is an operator and then this x is an operator, but notice in the last term we don't have any operators. So q is charge, our E is electric field, which is a constant, right? And then our m is mass and omega is frequency. So we don't have any operators in this. So this is like a constant. So what I did was, let's say if you have your uh, Hamiltonian, which is some h naught, another Hamiltonian plus some constant c, and if I do h psi, here, if I operate it on some wave function, right, h naught psi plus c times psi. And if I know the eigenvalues of this h naught, let's say this is our harmonic oscillator wave function, right? I know the eigenvalues, so I can then directly write them as h cut omega n plus half times psi, and then this is some constant times psi. So essentially, I can just take this constant here and multiply this with psi. So the eigenvalues of h, if you notice, is this thing, right? So whenever we have a constant energy term in our Hamiltonian, it just comes out directly here. So same thing. So these first two terms, this is our h naught, which is the Hamiltonian of a simple harmonic oscillator, with only difference being that now instead of x we have some shift in x, so x minus x naught, right? And this last term, it is a constant, it does not have any operator in it, so we can just directly add this thing to the energy eigenvalues of our harmonic oscillator. Is that clear?
Yes, sir.
Okay, good. Okay,
But
yeah,
does that mean shift in the center of the harmonic oscillator? That is
correct.
not to introduce any perturbation.
Sorry.
The x is now changed to shifted to x minus x naught.
Yes, so generally, okay, earlier, okay, when we, let's say, I'll give you an example of a pendulum. Okay, you can try to visualize this thing. So let's say we have a pendulum which is also charged. Okay, so it will react to your electric field, right? And it is oscillating. Okay, it is oscillating. So generally its equilibrium position is at x is equals to 0, right? But now imagine that you have applied an electric field along this direction, and this has a charge plus q. So now its equilibrium position will not be x is equals to 0. So earlier if it were oscillating like this, now because of this electric field, so electric field is here, your gravity is here, so it is experiencing some net force along this direction. So instead of this being its equilibrium position, it will have some different x which is not 0, right? So it will, instead of oscillating like this, maybe it now oscillates like this. So then this is the equilibrium position.
Okay.
Yeah, so there is a shift in the equilibrium position of our oscillator.
It's like adding a phase constant, cos omega t plus phi, something like that, in the harmonic oscillator equation. Just the
Yes,
harmonic oscillator.
phase. So uh, phase does not change necessarily your equilibrium position. Phase essentially changes what is the position at time t is equals to 0.
Initial position.
Yeah,
Okay.
initial position. Equilibrium position generally changes when you have some additional force coming into picture,
Okay.
right?
Hmm.
Yeah. So here we have an additional force coming because of our electric field.
But no change in energy because of this additional force.
Huh, there is change in energy. See, earlier we had only this first term. Now we also have to take into account the second term.
Okay. Good.
Okay. Yeah. Okay. So final problem, which is a very straightforward one. True or false? The expectation value of a physical observable O, for example, energy or momentum. So it is given that in Schrodinger's representation, it is this, and its expectation value in Heisenberg's representation is this. So the problem is either they are same or different. The question says that they are same and asks if this statement is true or false. So is it true or false?
I think expectation value should be the same, irrespective of which theory you go for.
Yeah, exactly. So yeah, expectation value is what we observe, and does not matter if we use Schrodinger's representation or Heisenberg's representation, we should get the same value, right? So it is true. So yeah, so that's it for today. That was the last problem. So if you want to leave, you can leave, and then we can continue our discussion from last class, which is not quantum mechanics but classical mechanics. And yeah, we were discussing Poisson brackets, and later we'll bridge the gap and we'll try to relate it to quantum mechanics. Okay, so the problem solving session is over, and we'll now look at some Poisson brackets. Okay, so I'll start. If you want to leave, feel free to leave. Okay, so we won't be solving any more problems. Okay, so in the last class we defined our Lagrangian like this, where T is the kinetic energy and V is the potential energy. We also defined that our conjugate momentum is this thing, right? And our Hamiltonian H, which is generally T plus V, or it can also be written as Qi dot Pi minus L. Okay, so this is Hamiltonian. Now in form of Hamiltonian, we have these two important equations. So Qi dot, this is del H by del Pi, and Pi dot, this is minus del H by del Qi. Okay, so I'm just writing some equations which we will use later. Just note that this Qi is like a x coordinate and Pi is like the momentum coordinate. Okay, and we call this as conjugate momentums. Okay, so Qi dot will be like velocity and Pi dot will be like force, right? This is like dp dt, which is force, and you can already see that this is like a gradient of our energy, so minus del v, right? So something along those lines. So this is like velocity and this is like force. Okay, not exactly but dimensionally. Okay, so we also defined that if we have uh, two functions a and b, then their Poisson bracket, this is defined as sigma I del a del b del qi del pi, and then minus of opposite, so del a del pi del b del qi. Okay, so this is the Poisson bracket, and it has some properties which are easy to see. That first of all, that it is antisymmetric. So b comma, if we do b comma a, we'll get minus a comma b. Okay, and now why this is important? This is important because like for from Newton's law we get the equation of motion of a particle, but when we are doing this Hamiltonian or Lagrangian mechanics, the time derivative of any physical quantity a, that is defined by this Poisson brackets. So dA by dt is given by a comma h, where h is our Hamiltonian and partial derivative with respect to time. Okay, now this is what resembles with our Ehrenfest theorem if you look at it neatly. Yeah, now this a can be anything, like any function. It can be position, it can be your momentum, doesn't matter, right? Okay, so one thing to notice here is that if your a does not explicitly depend on time, if del A by del T is 0, right? And your Poisson bracket is also 0, then our dA by dt will be 0. So we call that A is a constant of motion, right? Meaning that it is not changing with time. Okay, so there is no change in A with respect to time. What are the two conditions? That it should not have any partial dependence on time, and it should not, oh, and its Poisson bracket with H should be 0. Now, when we go to quantum mechanics, the only change that happens is that this A comma H, this goes to 1 by iota h cut and the commutator. Now here we have operators, right? And instead of just the value of A, we have the expectation values, right? So also our A goes to the expectation value, and del A by del T, this also goes to the expectation value. So this we already derived in the last class. Yeah, this we had already derived. Okay, so let's look at the force equation. Okay, so if A is P, so what do we get? We get this dp dt, right? Iota, sorry, 1 upon iota h cut, 1 upon iota h cut, and then we'll have p comma h. Yeah, and now if we, okay, if we write h as p squared by 2m plus some potential v, so p will commute with p square, so that term will vanish, and essentially what we'll be left with is, we'll be left with this term minus del v of x, right? And we know that this is like force, right? So this also in classical mechanics, if we just find out the Poisson bracket of P and H, okay, here. So okay, let me do this quickly. Let me take it down. Let us solve one Poisson bracket. Okay. Okay. So let's find out what is P comma H. Okay. So we are just considering a single particle motion in one dimension. Okay, just the x-axis. So this summation is not required. So what will this be? So this will be del A. Oh, okay, instead of A, we will have P, del A by del P. Sorry, del P by, so Qi I am writing as x. Okay, and then del H by del P minus del P by del P and del H by del X. Okay, so this is what we will have. Now, of course, P does not have any direct dependence on X, so this term goes to 0. So we can write, and this will be 1. So this is just minus del H by del X. So let's write H as T plus V X, and again only this V is a function of X. There is no X function in the kinetic energy. So kinetic energy goes as P squared. So what we will be left with is minus del V by del X. Okay, and this is nothing but dp dt, which is force, right? Dp dt. So this is the Newton's second law, right? This essentially tells us that the Newton's second law and this equation of motion, this one, this equation of motion, they are both one and the same thing. But this equation, this is more general, right? More general, because it not only tells us how our momentum is changing with time, but it tells us about any quantity that we wish to see as a function of time, right? It can tell us about position, velocity, energy, and anything. One one very quick thing that we can do, we know that H is our total energy, it is T plus V. So this Poisson bracket will always be 0, right? So this will always be 0. And if our energy does not depend on time directly, right? It does not depend on time directly. So our energy will be a constant of motion. Like we have considered, for example, many problems like simple harmonic oscillator, for example, or a pendulum, right? So there we know that our H is just p squared by 2m, and then plus half m omega squared and x squared. So if we again do h comma h, so this term will be 0, and you can see there is no time function. So h is not a function of time. So this del h by del t will be 0, which means that our dh by dt is 0. So our energy is conserved, right? Now you can do the same thing for a problem where your momentum has no time dependence, for example, right? Like like a free particle, or like a mm, particle just floating in space, right? So it has just some velocity v, and there is no force to change the velocity v. So again, what you can do, you can find out this commutator of. So essentially, what we'll get this same thing. We'll get we'll get this thing, and because our v is 0, so this second term will also vanish. We don't have any potential energy in space, right? So this second term will also vanish, and then what we'll get that our dp by dt is also 0. So there is no net force, and our momentum is a constant. So okay, what do we understand from this thing? So one is, this is just like Newton's second law, but a more general kind of a thing. Newton's second law only tells us how momentum changes with time when there is some external force. But this equation of motion applies to other quantities as well, not only the momentum, right? So this is just the equation of motion. It just happens to have a Poisson bracket inside it, and Poisson bracket is nothing but this mathematical relation, right here. And when we do quantum mechanics, if we make these changes, and this is what we derived in the last class from purely quantum mechanics, uh, we did not consider any classical mechanics, but what we ended up having the same Ehrenfest theorem equation, right? Which was this thing. What was that? Yes. Yeah. So quantum mechanics also gives us this thing, and classical mechanics we have seen gives us this thing. So Ehrenfest theorem is therefore considered a bridge between classical and quantum mechanics. Yes. So now you can ask if you have any doubts that you want to get cleared.
Thank you, Madam. That was good.
Okay.
Thank you.
Okay. If no doubts, then yeah, it's already time. So then we can end today's session. Okay.
Thank you.
Okay. See you all next Saturday.
Thank you.
Yeah, you're welcome. Have a good evening. Bye bye.